So we've spent about 2 weeks talking about composition of functions. Just completely abstractly, taking two random functions, composing them, meaning they didn't have any meaning to them. So when we talk about applications of the composite function, we're talking about, hey, we're going to compose functions, but there's going to be a reason why we compose them, okay? And so where this ends up applying, a lot of times in the real world, you have a quantity that depends on a variable. And then that variable also depends on another variable, meaning something else that changed. You have one thing that's changing as something else is changing, right? You have two direct equations that relate those things. We compose these two functions. What we end up with is we end up with a single equation that connects the two endpoints. Okay, you think about it like we're going to eliminate the middleman by doing the composition. So when we look at all these problems, we wouldn't necessarily have to do this as a composition every time if we just wanted to find specific answers. But if we wanted to model this so we could see how this is changing overall, relate the two end variables, this is what we would do. So let's do this example. I think the example helps explain it more than I do. Suppose an oil tanker is leaking oil. We want to be able to determine the area of the circular oil patch around the ship. It is determined that oil is leaking from the container in such a way that the radius of the circular oil patch around the ship is increasing at 3 feet per minute. What will the area of the spill be after 2 minutes? What will the area be after 5 minutes? Now, with the information given here, you could solve these first two parts pretty easily. Well, I could figure out the radius itself after 2 minutes and then use that radius to find the area of the circular spill and find that answer. The one that we're really after is the last one, after 2 minutes. Because I want to be able to figure out how can I just find any time and plug this thing in. And I want you to think about why this is a composition. So let's talk about some conclusions here. We can make following statements. The area of the spill is determined by a circle, right? How do we find the area of a circle? Area of a circle is pi r squared, right? Given formula. So as long as I know the radius of the circle, I can figure out how much area it's encompassed, how much of the water is covered in oil. But I'm also given something else. The radius is changing in this problem based on time. It keeps increasing. I know that the length of the radius is going to be 3 times the time. It's going to increase by 3 every minute of the spill. These are two independent functions. Length of the radius of your circle is dependent on how long it's been since the spill started. And that's an easy one that you could easily think about if you're standing on the ship trying to measure this. That's an easy thing to measure. You measure from one end to where you are, and you could easily see that radius. And then you could use that to find the area of the spill each time. That's how we would use these two things together. But we're going to write these things as equations. These two things turn into two separate functions. The area, which is based on the radius, pi r squared. Now the radius on this problem is based on time because it is getting bigger the longer we let oil leak out of this tank. If we want to answer this last part, we're going to need to compose these. And let's do this in our head to think why. If I wanted to answer 2 minutes and figure out how big the spill is, you probably wouldn't use a composition directly. You would say, well, at 2 minutes, 3 times 2 is 6. When I take that 6, that's now the radius. I plug this thing in here, 6 squared, it's 36 pi, which is whatever that is when we multiply it out. That's how you would find each individual answer. But by doing that one time over, it also helps you understand how we're going to compose these. This radius is dependent on time, meaning I'm going to need to plug time into this formula here before I substitute it in here. I'm actually doing a composition by applying into one function and then using that answer into the next one, even though I didn't even realize it. When we compose it, we can actually find its it's stuff at any time. So we're going to compose these two. And we kind of figured out why we need to compose them in the order that we do, because that's the other thing. It's helpful here because area is based on radius, radius is based on time. So if I want area from time, I need to insert the radius and get rid of it in the equation when I compose it. If I had tried to do this the other way, variables get funky, but if I used x and y, you'd actually end up with an equation that if you know the area of the spill, you can work it backwards and find out how long it's been leaking out for this particular problem. So you do need to pay attention to what order you want to compose these things in based on the problem, okay? Because they are going to give us different results because now all our variables have meaning. This is where it's a good idea to get away from doing everything as x and y and start using the variables in the equation. R is radius, A is area, T is time, so that you can see how you want to join these things together. So we know this just explains why I'm going to compose them in the way that I'm going to. So by composing these, we're actually going to find the last part first. So we know we want to compose them in this order. I want A of R of T because I want the area after some amount of time. You can see kind of the variables all listed in the right order. Well, R of T was 3T. And then if you plug that into your area formula, we get pi 9T squared. I'm sorry, pi 3 quantity 3T squared, which turns into 9 pi T squared. On a side note, as we move forward, never ever round pi. If you ever end up with pi in any sort of equation, write the symbol pi and use the functions in the calculators, okay? Usually it's not going to make a big difference, but when you write equations, you don't want to simplify that out. And especially as we work from here into, we're going to get into some trigonometry later, second quarter, and it becomes real important, the idea that we don't round that pi, okay? So what we just found here, this is the area of this spill after time t. So the area is equal to 9 pi the time since the spill squared, because we knew how the time since the spill was related to the radius and we subbed that in. So this is actually the answer to the last part. And then we can use that to find answers of the previous stuff. So if we use our 9 pi t squared, if I want to find it 2 minutes, I can plug into this, and you'll notice I said it was 36 pi the first time when we did it in our head. We're going to plug in 2. T squared is 4. What's 4 times 9? We get 36. You'll notice that we got the same answer that we did when we kind of just quickly calculated that, which makes sense. It also lets me know, hey, I did this right. And I actually wrote the rounded. It's 113.10 feet squared. We do the same thing for A of 5. 5 goes in. You end up with 225 there, because that's 25 times 9, which is, now, here's what we're really looking at here, okay? And we talk about the reason that this composition function and the way that it changes is important. Because this area problem, and it's a circle, this is a difference of 3 seconds, right? That's a pretty big jump in the area of this thing. Let's go 3 more seconds and see what happens. 9 pi 8 squared. 8 squared is 64, right? So 64 times 9. So that's 576. Somebody double check me on a calculator.
Yes.
Is that right? Cool. And what is 576 times pi? That one I'm not going to try to do in my head because, well, I'm going to do it on the calculator too because it's a good thing for me to show. So 576, oops. That's not what I wanted. I wanted Desmos. So was it 576 pi, right? Here's my pi on this thing. There it is. 1,809.56. Is the area of this spill increasing constantly? It's increasing by the same amount every 3 seconds? It's actually it's encompassing more and more area as the time goes on because of the shape of the spill. Okay, area and length don't have a one-to-one correspondence. It's kind of like area and volume don't have a one-to-one correspondence. Since it's based off of length, as that length is increasing, the area is actually increasing much faster because we end up with a squared in its composition formula. What I'm saying is the composition and knowing the formula for it will allow us to predict where it's going to go and allow us to understand, say this was an oil spill and we needed to stop it. We understand that time is an important factor here because this thing's going to get huge the longer we let this, and I put seconds, this should say minutes, I'm sorry. That was 3 more minutes. Anyways, this thing's going to continue to get huge, and then it's going to get really, really big the way that this thing is leaking, okay? And it gives quick ways to manipulate and talk about that number. You understand the composition and how to use it? Let's try this one together. So this says the volume of a balloon is given by V of x equals 4/3 pi r to the third, which is the volume formula for a sphere. So it's saying that this balloon is a perfect sphere. The radius is increasing with time in seconds, according to the formula r of t equals 1/2 t to the third. What will the volume of the balloon be after 3 seconds, 5 seconds, and t seconds? Now, if I asked you to solve just these parts right here, the 3 seconds and the 5 seconds, we could do that without the composition, but I think doing one of those in your head helps you get to where we really want to be, is this equation that models the way the volume of the balloon changes over time. If I asked you to find 3 seconds, well, you know that you need to find r, to put r into the volume. So you would say, well, r after 3, because the only way I can put time in is in the one that has a t. So this is 1/2 3 squared. So that's half of 27. And half of 27 is 13.5, right? So what that means is at the moment of 3 seconds, our radius is 13.5, and then we would plug that into the volume formula. And I'm not even going to finish this one because I'm not necessarily worried about the answer here. What I'm worried about is when you go through and you actually do this one step at a time, this tells you the composition. Well, because I needed to do this one first and then use the answer here, that means I want V of R of T to express this volume, because I want the volume based on the time. Since I need to use the time to find the radius and the radius finds the volume, you can kind of work part of it. This means this is the order I need to compose these functions. So let's actually compose them and see what happens. And then we'll use the equation. So V of R of T, so that's V of 1/2 T to the third. And usually what will happen is the math and the calculations will get a little bit easier when you compose them because you'll be combining some operations together, but not all the time. So this is 4/3 pi 1/2 T to the third to the third. So everything in this, the fraction top and bottom and this are going to get that third. So what happens is we need to distribute that third to everything. So this is going to be, and there's times in between all this stuff. 1 to the third, 2 to the third. Third to the third is, you're going to multiply those things, you're going to get to the 9th. So we get 4 thirds times pi times 1 over 8 times t to the 9th. Does it matter what order you multiply in? Now you multiply in any order. That's why we're going to combine the fractions together, simplify this thing out. So we get 4 over 3, and we're going to do 1 times 8. That's what I want to simplify. So this is, and then it's going to be pi and t to the 9th. There's an equal sign, sorry. So 4 over 24 pi t to the 9th. Common factor 4 and 24 is 4, right? So that's 1 over 6. So it's 1/6 pi t to the 9th, which is a whole lot easier fraction to deal with. Only thing that you're going to probably see if they want you to find an equation this, they're not going to leave 1/6 to the 9th. This is also a fraction. So that pi goes on top, that 6 goes on bottom. So the volume at time t is defined by whatever pi over 6 is, which is a number, times the time to the 9th power. And that is our equation that models volume after time. Then we could use it. We're going to get the same answer we'd get up here. So then the volume after 3 seconds should be pi over 6, 3 to the 9th. So let's actually do that one. So pi divided by 6 times 3 to the 9th, 10,305.99, right? What you got too? So that's, at that point, if we're, let's say we round it to 2 places. So it's going to be 10,306 because you're going to get zeros after that. So it's 10,306. And this is inches, right? It doesn't tell us. Let's say it's inches. It's a big balloon. We use this formula with 5 and do the same thing. Plug in the 5. Find that particular answer. So the only thing that changes over here is this thing becomes 5, and we get, wait a minute. $1,306, that's right. There it is. 102,000, I'm sorry, 1,022,653. So 1,022,653. Let's see what the decimal was. 0.86. A lot of times what will happen is your inside function is going to be composed of time, something that's changing is time, and then something else we're measuring that's based on that thing that's changing by time. That's one of the common ways you'd see this problem set up, okay? Another one that you would see often is one like this. So let's say you were buying a new 4K TV for your birthday because you received a $25 off coupon in the mail. When you get there, you find out that all TVs are on sale for 15% off. You find out you can use the discount and the coupon for your purchase. Both of them. Which order do you want to do that? And notice, do I tell you how much TV cost? So that means there's got to be some overall general rule here, right? So let's look at these things as functions, okay? Let's call P the price of the TV. And let's write two functions for this. So we're going to write one for the coupon. So let's call it C of the price of our TV. Price of our TV, and this is with, price of our TV is no coupon, no discount, nothing. This is MSRP, right? This is what the sticker says before anything else. So if I applied my coupon, what math would I do to the price to find it's what I'm actually going to pay for it? I'm going to take this price and I'm going to subtract 25 from it. But I also have another function here. Let's call it it's this percentage. Let's call it the discount. We'll call it D. It's also going to affect the price of the TV. And I get 15% off this time. So that means what percentage of the TV am I actually paying for? If I don't have to pay for 15% of it, I only have to pay for 85% of it. This is a multiplication, meaning if I took 0.85, remember percentages into decimal form, and multiplied it by the price, that would tell me the new price of the television. So I've got two functions here, and I want to know which way do I want to apply them. Do I want to do the coupon and then the discount? Or do I want to do the discount and then the coupon? And off the top of our heads, this seems like, well, this seems really challenging, right? Because we don't know the price of the TV. So we got to figure out, well, does this hold for all things, right? Does it work every time for no matter what the price of the TV is? Or is there a certain spot where, well, if the TV is only $250, I want to apply the coupon and then the discount. But if the TV is over $250, we got to figure out if that happens as well, because we want to make sure we save the most money. Let's find the composition of these things. So we want coupon, then discount. So that means the discount's the outside function. The coupon is the inside one. So to find this, we need discount of the price of the TV minus 25. That means we got to multiply this by 0.85. And let's finish simplifying that out. Well, let's leave it for a second. We'll come back to it. Here we want discount, then coupon. So the coupon's the outside function. The discount's the inside. So coupon 0.85 P is what gets plugged into it. So this P value turns into 0.85, and the 25's out here. So those are our two compositions. They look really, really similar, right? Let's actually finish multiplying this one out. 0.85P. Let's do that 0.85 times negative 25. So 0.85 times 21.25. So this is coupon then discount. This is discount then coupon. Which one's better? Well, we could plug some numbers in here and see what happens, right? But what I want you to look at when we figure out which way to apply these, we need to compare these two functions. Both of these things are linear functions, right? So one of them is y equals 0.85x minus 21.25. The other one is y equals 0.85x minus 25. And remember, the x is the price, the y is what we paid. What do we notice about these? So both these things are lines, and they're in slope-intercept form. And you got to think all the way back to Math 1 to remember this stuff. which is where I think this gets even tougher. So this is the slope of that line. This is the y-intercept where it crosses. What do we notice about the slopes of these two lines? They're the same. Do you remember what type of what special term we have for lines that have the same slope? Starts with a P. That doesn't help you much because when you learned it in Math 1, both your terms started with a P. These two lines are parallel. Anything with the same slope, any two lines with the same slope will be parallel. Okay? They just cross the x-axis a different spot. Let's actually look at these graphed and see what this thing looks like. So we had 0.85 minus 25. Got to put a y in there. No, I don't. It's just off the screen. And then we had 0.85, 21 1/4. Is that it? 21 1/4. I don't see anything. Where is it? It's farther out. There they are. And you can really get the idea that they're parallel here, right? The red one is that. So let's actually screen clip this so we can write on it. This is what our two graphs look like. And we know because they're parallel, those two lines aren't ever going to touch. Something that we know. Now, what we have to remember is when we set this up, the X value here, that's P, that's the price of the TV. So down here on this axis, we actually write the word so you can see it. We get the price or our cost of the television, right? Sorry, the price of the TV to start. Up here, what comes out, this is how much it costs to us after we get our discounts and our coupon applied. The red line, this was my discount, then coupon. The blue line was my coupon, then discount. If we look at this, this says if my TV costs $60. Now I know these numbers don't make sense normally. I don't think you're going to buy a $60 TV. But let's say our TV costs $60. Which way would be cheaper? Well, which line do we hit first? We hit the red line, then the blue line, right? Since the red one's closer down, it means it's going to have a cost that is less than the cost of the blue line. Is that ever going to change? No, because what do we know mathematically about these? We know that they're lines and we know that they're parallel because they have the same slope. No matter how far out I chase those lines, the red line is always going to be lower than the blue line, meaning because my y-axis is the cost to us, that means the method that I used to find the red line, which was discount then coupon, is always going to be better. And I can prove it to you when we drag this thing out further. You continue to see, no matter how far up we go, notice we're at a cost of $480 now, the red line is still lower than the blue line. And I promise you, no matter how far out you go, they're never going to cross. And we know that because we know that stuff about the lines. So which way do we want to buy this? Does it matter what cost our TV is? No, we want to do the discount and then the coupon. And the key to this lies in the only thing that's different in the whole equation. This right here. What happened to our coupon? This was our coupon right here. Because we took it, we did discount and coupon. Because we did the coupon, then the discount, right? We actually lost part of our coupon. We didn't get $25 off. We actually discounted our coupon as well. We ended up with 21 1/4 off instead of the 25 that the coupon promised, just simply because of the order we applied it. So some of the things that you can evaluate and look through, okay?